Okay? So actually I decided not to go too much further. Maika is worried. I'm not going to tell the story of what happened to the plateau today. I'll leave it for tomorrow because it's already a big step from wedge to plateau. So I think it's enough in terms of new concepts for today. So tomorrow will be what happens to the plateau. But we'll still go to the Aegean area, which is here. It's the same Africa, Eurasia convergent setting, but a very different situation with some kind of a mountain on the edge, Crete, and the Hellenic Trench, and then an intermontane basin and another mountain on the side here. So an intermontane basin. In terms of seismic tomography, it also shows one single plate subducting towards the north. But look at it here. Here it looks like it's getting overturned. And there, I don't think I think we can discuss for the Himalaya, Tibet, about the polarity of subduction, but here it's fairly well constrained. And that goes all the way to the core mantle boundary. So it goes across the transition zones of the mantle. Above that slab, you have a zone of low velocity beneath the Aegean Sea. So beneath the Syria, there's a low velocity zone that might reflect some kind of weak mantle. In other words, an astenospheric mantle. So lithosphere here, an astenospheric mantle. And we'll see that this might reflect slab retreat, southward slab retreat, which was actually first identified by the geology, not by the tomography. We'll see that in the next slide. And in this area, no mountains. So at first, same models as for Tibet or even the Alps, actually. I didn't mention them from the Alps, of continental collision, extrusion, except that here the free boundary is towards the west and not the east. And you see it's even more, I think it's even more compelling here. So the vector, that's GPS, and current day displacement. The vector goes from north-south to east-west and even south-north. The norm of vector decreases passing the topographic front, which means shortening in the horizontal direction, thickening in the vertical direction. And here, the norm of vector, when it passes from the Anatolian plateau, there's another plateau here, that's a plateau, an orogenic plateau. The norm goes from small to very big. Well, that's peculiar for a punch. If I illustrate it with a punch, it's like if you had the head going out before the punch. You're feeling that I'm going to punch you in the face, so you go away before the punch. This moves faster than the punch. That's strange. That doesn't match the punch. What does it mean? Well, here we have a high topography, low topography. So the transition from here to there, in the vertical direction, what happens? See if you followed. Horizontal stretching, vertical thinning. No punch. At first sight, it might be tempting to say, okay, that's extrusion, lateral extrusion toward the west. And there's the Anatolian fault here, which is the most active fault in Europe current day. So it's very important to have a simple model that explains that. Well, looking at it more carefully, you see, the punch hypothesis, I think, is not that relevant. And people then have worked on this area and have identified that there is actually horizontal stretching, many basins here. All these lines are alignment of basins, sedimentary basins. And it's been exemplified by cross-section, structural cross-section, with here the Corinth rift. The Corinth rift is this one. And there's a high-angle normal fault that here is proposed to root into a low-angle detachment. And in Naxos, that we're going to look at in details tomorrow morning, here in the middle of the Aegean, there is a metamorphic core-complex style with low-angle detachment and high-grade rocks exhumed beneath the detachment. So there is a lot of extension going on, crustal extension. Other than that, if we look at the geology, so I'll put some colors on that map. I put them some colors that correspond to geologic units. So it's difficult to represent because there are different issues to be illustrated here. So most of these rocks are Tethyan units, sediments from the Tethyan margin, or the continental margin of the Eurasia and Gondwana. The green ones are representing sutures. So that's one suture, which is called the Vardar suture to the north. And then here is the Pindos suture in the middle of the Aegean. So it has been debated whether these represents two different oceanic domains or it's the same that has been refolded and forming a single nap. I think now it's fairly, it's the main data confirm that it's two different oceanic zones separated by a continental ribbon here, another continent that's Eurasia margin, an ocean, a continental ribbon, another ocean, and another continental ribbon. And the oceanic crust is being subducted nowadays beneath the Hellenic Trench. In brown, these represent some of the basement of these continental ribbons, and they are Variscan. So they are inherited from the orogeny before the Alpine orogeny, the orogeny that built the European basement of Western Europe between 400. So it's from 400 to 300 million years. There was an orogenic belt that formed during the Variscan and is forming the basement of most Western Europe. So where was I? Yeah, and these rocks, so you have the basement, the Mesozoic cover, and these form these naps between two different sutures. The current day trench is here. That's the one that accommodates current day subduction. That's here. And in the rear here you have thrusts, like ophiolite on top of continent, that's a thrust. But you also have normal faults. All these with squares or ticks are normal faults. Thrusts are cross-cut by normal faults. And you have also high pressure, low temperature units that are in the dark blue. Here, 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 in Crete. But also high temperature, mid pressure, low temperature, low pressure units in red. So you have a transition from high pressure to high temperature. And the high temperature postdates high pressure metamorphism. And if we look at it in northern part of the Aegean domain, in Rhodope Massif, the high pressure is 70 million years. High temperature is 40 to 30. And is structurally below, separated by a normal fault from the high pressure. In the Aegean, what dominates is the high pressure, but there are some high temperature rocks that are exhumed in place to place. For example, here in Naxos, we're going to detail that tomorrow. Naxos here. And there the timing is 60, 55 million years for the high pressure, 20 to 30 for the high temperature. Another 20 to 30 million years delay between high pressure and high temperature. Same as for the Somorari and Dome region. You have 55 for high pressure and 15, 20 for 15, 20 for the high temperature. So a delay. So this will give us the opportunity to investigate the transition from low to high geothermal. And in terms of deposition, it's all the yellow. You have foreland basins, that's actually the brown, foreland basins. They are cross-cut by the yellow extensional basins. So you go from thrust-controlled basins, foreland basins, and then extension-controlled rift. But rifts very distributed. And it's all over the place. You have rifts, faults like that, faults like that. No, they also tend to be perpendicular to the, parallel to the convergence direction. Okay? That's for the setting. Yeah, that was the first evidence for retreat. This purple line, dotted line, represents calc-alkaline magmatism. And calc-alkaline magmatism is typically associated with subduction. And you know that alkaline or arc magmatism requires the plate to be subducted at a depth of about 100 kilometers, which controls the amphibolite-eclogite transition. And this reaction releases water that will lower the solidus of the mantle, generate magma that are put on place. So you know when you have arc magmatism that at that time, eclogite transition was at 100 kilometers below your feet. That's very convenient to reconstruct plate tectonics. So it was 40 million years here, 20 million years here, and it's today active. Santorini, very nice island, very touristic. Santorini is here, and it's active volcano today. 40, 20, 0. So today, the amphibolite-eclogite transition is here, and it feeds the arc today. It lowers the solidus of the mantle here, promotes magmas that are going up there. How to explain that it was there at 20 and there at 40 million years? Well, just the idea is that the plate retreated like that as it converged. So it was not only retreat, it was also convergence with retreat. Because we know that during that time period, from 40 million years to today, Africa has been converging towards Eurasia. So you can have convergence. My elbows are getting closer to each other, right? But at the same time, retreat. In other words, the point of contact is not fixed. I'll skip that. Okay, what about the metamorphic record of that? So we're going to go into the Cyclades, the central west Aegean domain, and we move from here close to Athens, that's the capital of Greece, the Lavrion area. I'm not going to show Evia, we have very nice results there, and we're going to move to Naxos. So first we look at this area today, and tomorrow we'll move to Naxos. So here we have represented, the Pelargonian nappe. Here, that's the Variscan basement, non-metamorphic during the Alpine orogeny, with pieces of the suture in green, the ophiolite nappe, and here contact with metamorphic rocks. That's the main contact with metamorphic rocks. So below, structurally, the Variscan unit, here you have metamorphic rocks that are alpine, and the protolith is mostly the Mesozoic sedimentary sequence, marble and schists. Where it's with blue lines horizontal, it's been only affected by blue schist facies, high pressure, low temperature. And you see there are some places where you have a superimposed metamorphism here with green lines, vertical, that corresponds to green schist facies superimposed on blue schist facies. Retrogression. You asked that the first day. What conditions retrogression? That's retrogression. And in some places, so for most of the Cyclades, it's the case, blue schist and then green schist. Some islands have preserved only blue schist. And then, when you have cross like that, with purple and purple, that's blue schist, fairly, only rarely preserved, but most of it is blue schist overprinted by mid-pressure, mid-temperature, amphibolite, or green schist to amphibolite facious metamorphism. And all the way to migmatites in the core here of Naxos. So let's start first with this part. So that's a zoom of that. The Lavrio, Lorion in French, Lavrio in Greek. I'm not sure you're familiar with that, but people who like minerals might have heard that name. It's a famous place for minerals. And it's been also the place where the Greek civilization, the Greek antique civilization, digged all their metals to build boats, to make coins, money. So it's full of holes everywhere. I have to be careful actually. When you walk there, sometimes boof, there's a hole like this, and it's not. There's no panel to say be careful. So you have to be careful. But actually, it was a chance. At first, we went there as a geologist, and we met an archaeologist interested in mining techniques. And that's another good example of interdisciplinary research. When archaeologists met geologists, was wonderful. We went down in the holes. We had to take all the helmets, the lights, and things. It was difficult for me. I had a hard time to go in. And you have an history of two periods of exploitation in the antique, and even much older than that. It was dated to 16,000 years ago, so it's very old mining. And then the Industrial Revolution picked up on top of that. There, the galleries are pretty big, so I can walk in it. But the antique, that's impressive. The antique, sometimes you're in a gallery, that was digged for the Industrial Revolution, and you see just a hole like this 1 meter by 1 meter square, and these guys went inside. Well, I could go inside, and I couldn't go down, back. I was stuck. And you see you can still see the trace on the walls of the guy that has been. That's impressive. And so we started to build a project that was not fully funded, unfortunately, but I thought it was very, very compelling with archaeologists, with the guy that was looking at the morphology of bones of people that worked, and we could find their bones, and you can find that they had very casualties on the shoulders, on the forget my names. They're everywhere. They had and so you can tell the condition of life of these people working in these mines, 2,000, 3,000 years ago, and then the evolution also with methodology of ore extraction. It changed from fire-oriented to more crushing and then valorizing it outside the pit. But still, what we managed to do is, us geologists, because the guys that were doing archaeology, they would follow all the galleries and do a map of it, precise 3D map of that. And when they showed it to us, we identified the geology. And I'll show it to you indirectly. So what's happening here? So we have here a blue unit made of marble and schist, mostly blue schist. And a green unit that is in contact with the blue unit with here a red contact. And you can tell by its shape that it's fairly flat-lying. It's almost horizontal. And the blue is on top of the green. So these are clipper. And the green is mostly green schist facies, marble and schist. The same potolith, different metamorphic grade. So if you look at it on cross sections, it looks like this. So you have marbles folded and refolded with the schists. on top of marble and schist, folded, refolded, but with mostly green schist-facious minerals. These were blue schist-facious with glaucophane, chlorite, fungite, epidote. So that's in a metavolcanic, which is this, which is actually this one. And here you have mostly chlorite and fungite, so low-grade green schist-facious. And on top of that, you have the ophiolite map that is non-metamorphic. So we're not now going to look at the structure. So the structure is it's not too much vegetation, so you can draw panoramic view. And what the technique, for field geologists, I think, is to do the work in two different scales. When you have this type of area where you can read into the scenery, draw the panorama as well as you can from your interpretation, and then you're going to walk there and check if it's correct, and take measurements. And once you are there, you turn around and you make the panorama of where you were the day before, where you had taken measurements. So you have to make things in two steps. From far, and when you're far, you look at the rocks where you are standing, making measurements, and then you go where you, on the outcrop, turn yourself and make the panorama of the day before. So it requires to have good notes and a good memory. So this is why I could attest that we have a superposition of S1 related to F1, S for schistosity, F for fold, refolded by F2 with an axial planar schistosity S2, and refolded by F3 with an axial planar schistosity S3. So this doesn't show in the first glance from the panorama. So you have to take measurements then and make observations, detailed ones. So this was done throughout this area. I'm not sure we see all the data. No, it didn't represent all the measurements, but we pretty much covered everything here with measurements, structural measurements. And that's 50 kilometers by, so that's 50 by 50 kilometers. So these are the outcrop features. And if you don't look carefully, you might miss it. You say, okay, it's all the same schistosity. You have to pick up contrast in rheologic contrast between different layers. Here's more carbonate-rich layer and more mica-rich layer. And if you look at it carefully, you find this type of hinges. That's an F1 fold. And you see that if you follow this layer, it's folded here. It's folded here again. And this is not the same hinge as this one. So you need an F1 for this one and an F2 for this one. You need an F1 and then an F2 and you have to find the place where the F1 is preserved. Is that clear? Take some time to get your eyes used to it. Actually, the first time I did that work was doing my PhD. I invited my master supervisor, and we were in front of a panorama like this. I says, okay, I think there's F1, F2, F3. I say, stop, I don't believe you. He say, okay, I'm going to spend the day in the bar, and you're going to map this area, and we discuss it in the evening. He was right. I took all the measurements and made all the. He was right. I was say, okay, that's experience. Maybe one day I'll gain that. So it's a matter of repeating these observations. Once you see it once, then you see it everywhere. By the way, I come back to that. In the previous models here, that was the trend in the 80s, 90s, 2000, and even now, is to look for these myonanites. It's very important. I'm not saying it's not important. These myonanites that mark very strong contact, localized deformation between units with very different histories are very important to identify in the field. What is the assumption here is that all the rest is rigid or non-deforming. See, these are blocks These are units that do not change shape, or almost not, a little bit here. When you look at these units, you find F1, F2, F3 at least. It's not continuous, it's not, it's very deformed. And this deformation tells you something that I'm going to expand on to now. So another example here with this marble and schist. So I drew that. So here it's not easy to find, but you see here an inch. And it's refolded here, so that's F1, F2. And you see here a pattern of horizontal folds. So it's F1, F2, and F3 on one single outcrop. Well, not sure it shows very well. I think it's better from far. So you see it here, this, and you see here that. Better example, but it's here only S2 and S3. S2 and then S3. Another one with F2 and S3 with gradients of transposition. Here the S2 is better preserved, and here you only see S3. And you have to catch these in the field. That's part of the structural analysis. And then what did we do? Well, we sampled the F1 fold hinges, the F2 fold hinges, trying to see if we could detect obliquity between S1 and S2. That's the key. And then between S2 and S3. Can we find that in the thin section? Yes, we can.
Can we say that the lineation of fold 1 and lineation of fold 2 are...
Axes, you mean, axes.
Yeah.
Yes.
They are perpendicular.
Yes, okay, good point. When you have this type of fold interferences, that's called hook type. That means that the fold axes are parallel between F1 and F2. That's one possibility. But you can have everything between parallel or perpendicular. And perpendicular will give you, egg box type of an interference pattern, or domes and basins. And if it's oblique, it's crescent shape. So here, I think we're lucky because the crescent shape is difficult really to decipher. Hook type is the easiest to identify. So we're lucky, and we'll see it's not by chance. We'll see that has a tectonic explanation. But it's a good point. Thanks for raising that. So can we find it? Yes, we can find S1 and relics of S2, and mostly here S3. And you see it's not underlined or delineated by the same minerals. But that's tricky. That requires a mapping, chemical mapping, of this. So we come back to that afterwards. But do you see the different schistosities marked by different minerals? So then the idea would be to pick up the composition of the minerals delineating one structure, and pick up the composition of the minerals delineating another structure, and see if they reflect different pressure temperature conditions. Wow, that's a lot of work. Very precise work. And you see it requires also even statistical analysis. Yeah, and the basic underlying assumption, so we're going to work here with chlorite muscovite. So it's chlorite muscovite. Basic assumption is that minerals that are in contact, at their contact, they are in thermodynamic equilibrium. They have recorded the same pressure temperature. Inside these minerals, there might be not quite, there might be a zoning from the core to the boundary. So X changes, the composition changes, and the one that is at the contact should be in thermodynamic equilibrium with the minerals that is next to it. The one that is in the core might represent another equilibrium that was preceding the one at the contact. So this is the reasoning. The problem is that here you see I draw it with minerals that are circles. Micas are not the best for that, because micas, they are made of foliates. And catching the zonation in minerals like that is not as if you had a concentric zonation. The zonation is very much controlled by the foliate. So it's difficult to get the core and the rim. And we'll see that's the main limitation of that reasoning. So we'll come to how to exploit that mineral assemblage structure relationship in terms of PT conditions and path, PT1, PT2 with D1, D2, D3, and then how it relates to a tectonic scenario. We'll do that in the next few slides, but before I finish the geological tour. So we have the detachment. Look at that. That's this line. So on top, that's this, the blue schist with some volcanic rocks, basalts some basalts here you can still see the pillow. And when you break the pillow, you find glaucophane in it. So the rock has not been deformed, but glaucophane, which is the high pressure mineral, grew without deformation. So you find that here. And below that surface, you have the green schist. So that's the cross section. And when you go there, you have actually a gradient of deformation over a few tenths of meters, and then a sharp, very sharp contact. You start with malonite in the marbles with dolomitic layers that are boudinaged and asymmetrically deformed, with the asymmetry of the tails giving you the sense of shear. And on top of that, you have the same marble that is broken into pieces. So it means that we go from malonitic, ductile, to cataclastic, brittle deformation. What does that represent? When you go from ductile, and ductile is superimposed is overprinted by brittle. So in terms of temperature and pressure, what do you think it means? Decreases. And is it consistent with burial or with exhumation? I love that. You're much better than my students. I'm going to stay here. Probably I've got some Indian mood. Because I never connect like that with my students. Never anymore. It's strange, huh? No, I'm really happy with that. So let's go back now to at first, we followed that logic. And actually, just what happened, just in a few words, in terms of a human relationship. So we've been working with my friend and colleague Stéphanie Duchesne in Naxos since 2000 to 2010. But then we published, but not as much as we wanted. And there are other teams that were in very good pace and were ahead of us in terms of competition, scientific competition. So we decided to change area. And there was one student that came to my office, and he was finishing his bachelor, and says, okay, where can I spend good holidays doing both party and geology? I say, go to Greece. If you go to Greece, it's going to be hot in the summer, but you're going to have fun, and you're going to have very nice rocks on the beach. So he went there, and I say, okay, if you bring me back a few interesting samples, we might define a master project for you. And that was his master project. But he was not lucky, because at first we followed that strategy, core and rim, and didn't yield any result that was understandable. So what we did is to do a very precise mapping of these minerals, chemical mapping with the microprobe, the electronic microprobe, with one spot every, I don't remember the resolution, but it was for one mineral like that, you'll see you have tens of points. And this is the result. So here it only shows, so these are the white micas. And so that's 1 grain here, and these are the chlorite. White micas, chlorite. So I have 1 grain here, and see, boom, 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 boom. Every spot is an analytical spot. And even with these details, it's difficult to see zoning. And if you plot that into muscovite, pyrophyllite, celadonite, these are the different poles of the white micas, you see a shotgun, right? The analysis, these are the analyses. So that's where the trick is. You say, okay, from that very complex cloud of analysis, I'm going to make it simple. And that's a bit, I think, sensitive. Okay, let's say that all these that are in this corner, I know where they are, the position of these points. I put them in light blue, all the light blue. We say that all these are the same. And we do the same for these, the dark blue. That's the dark blue. And these are the green. Okay, and that starts to be more organized. Even though you can see there's a continuity in the analysis, you pretend it's discretized into 3 different compositions, which is wrong, right? We know. Myself, I was not convinced of that strategy when the guy that we were working with proposed it. I said, I don't like that, you know. But still, we identified that the green, okay, can you see it? Where is the green compared to the blue? Is it outside or inside? So who's for inside, who's for outside? So inside. Inside. Outside. So see, that's not that obvious. Huh? If half and half, and third and another third doesn't want to express himself or itself, it means that it's not that clear. Okay, we managed to convince ourselves that this one is inside, surrounded by blue. You might not be convinced. Discussion, debate. It's good. Oh, it's good. Same here. We managed to convince ourselves that this is inside, surrounded by blue. Same here. But it's not that obvious. I agree. Yeah? And that's where, in the thin section, you have the S1, S2. And actually, you'll see why, but I designated the green as S0. But I am not going to give you the explanation now, just a few slides afterwards. So for the chlorite, same. Difficult to tell which is into which, but okay, we tried to convince ourselves that this was S1 and this was S2. And that's for the unit that is on top, the blue schist. And the blue unit that is below, that's the one. I think there it works better. You have the... still, it's not... So the blue is supposed to be... The dark blue is supposed to be S2, and the light blue is S3. And I think it's right that here you have more dark blue than here. No, it should be the other way around. See, I'm not even convinced. Sorry, I'm too honest. No? But we managed to get that published too. Or did I make a mistake? Because I just relabeled them this morning. Let me check. One, two. Yeah, that's right. Okay. So that's 2 and 3. Okay, I made a mistake. That's why. Because, I mean, I'll tell you the story. Because Christoph Schäfer, who did his PhD on that, he labeled them 1 and 2, even though they represent S2 and S3. I mean, okay, you're honest, you only see 2, so you label the first one 1 and the second one 2, but we know from field relationship that what you labeled 1 is already 2. So how are you going to explain to anybody else what you're doing? You know, if you label the second one 1, then the third one 2, that's not going to work. So I relabeled them. And did I do the same mistake here? So that's, yeah, same mistake, okay. So that's 2. And that's 3. Don't try to work too early in the morning just before the lecture. Okay. But that's a good test. No? Good test, and it was not working. Yeah, something wrong. So there's more light blue here, that's S2, and more dark blue here, that's S3. Whew. And S2 is better preserved in the chloride, in the core of the antiform, rather than on the flanks, where it's S3. That's much better. Huh? You're better convinced? So now what does it do? What we can get is what we call isoplet in the pressure temperature field. And what were we after? We were after finding the transition from high pressure to high temperature. So going from the blue schist to the green schist. What were we expecting? An increase in temperature going from S1 to S3, right? So we had a preconceived idea. And that's important because you'll see. So what happens? Well, the first micas, the ones that are Porphyro class, here, the green ones. They are here. So that's, they can be anywhere along this equilibrium line. The composition of this white mica can be anywhere, and each line represents one mica. So that's a range of micas that can cover this full range of pressure temperature. But if you compare them with S2 and S1 and S2, these ones are on the higher temperature side. So the earliest ones are on the higher temperature side, which is the contrary to what we expected. So then I thought, because I'm used to make wrong reasoning, so I thought, okay, maybe I did something wrong in my reasoning. But then I had a lightning. Muscovite resists alteration, supergene alteration. What if this muscovite was a Variscan muscovite, not a metamorphic one, but a detrital one, coming from a Variscan granite that was eroded to feed that sediment? And the Variscan granite will yield high temperature muscovite. That's why I called it S0. Could find a solution to explain the data. And then you have S1 and S2 with decreasing pressure from S1 and S2. But fairly high pressure, low temperature field. And you mix that with the temperature given by the chloride. So we are here. The chloride gives the temperature. It's something like around, doesn't change much between S2, I forgot to relabel these ones. So that's S1 and S2. So there's a slight decrease in temperature. Yeah, that's this one. For the green schist facies, so the bottom unit, there you see a clear increase in temperature, going from S2 to S3. That's S3. So there's a clear increase in temperature. So there we are in business. S1, S2, slight decrease in temperature with decrease in pressure. That's at the higher structural level. And at the lower structural level, from S2 to S3, increase in temperature with decrease in pressure. So now we can put that into D1, T2, D3. So these are Hercynian grains, detrital grains, D1, D2, D2, D3. Let's put that into a pressure temperature path. So that's this study. So the upper structural level only recorded burial, peak metamorphism, and exhumation with a slight decrease in temperature, while the bottom structural unit followed pretty much the same trend up to S1, S2, and then a slight increase in temperature that corresponds to S3. We have demonstrated the transition from high pressure to high temperature. And then we can translate that into pressure, temperature, time, deformation, path, D1, M1, D2, M2, D3, M3. So how does that translate into a tectonic scenario? So this is the proposition, is that D1 records burial and asymmetric folds associated with burial as the F1 folds. F1, and then the F1 are overprinted by F2 with a reversal of the kinematics. And F3 is transposition of high pressure into high temperature. So F1, burial. F2, exhumation along the same channel with reversal of kinematics. That's still there are rocks that have been buried at the front. And the reversal of the kinematics happens inland with this high angle, so that's a steep dipping detachment. So that's, if we name the structures, this is a thrust. And this is a high angle, not a low angle, high angle, steep dipping detachment. And this is the last structure, which is low angle detachment. And this structure that most structural geologists and tectonics would call an extensional structure is actually contributing to build the orogen, associated with exhumation of units that have been decoupled. It's not very well drawn here. But I wouldn't draw it like this exactly, but still I think we can get the point. And then there is the last stage, still associated with retreat, that corresponds to low angle and post-orogenic extension. And this contributes to thinning the crust. This contributes to thickening the orogenic crust, even though it's an extensional shear zone. That's why I don't like these terms. And that's the superposition that we just drew, S1, S2, and S3. And during that period, there is burial and exhumation under low geotherm that preserves high pressure, low temperature rocks. And then at depth, so the high pressure, low temperature rocks are better preserved at the higher structural level. And at depth, the temperature increases, and that's where this transposition will occur. First with green schist facies, and tomorrow morning we'll see how it goes into amphibolite facies, even all the way to partial melting. And there you barely see any relics of this high pressure. Okay? So the last slide, this also allowed us, when we went into that's in the caves, in the galleries, allowed to find S1, S2, S3, and pyrrhotite, and also different type pyrite, different type of mineralization. So we could place the ore deposition into that tectonic framework. So we could find the primary ore that has been then reworked, and this has to go with the fluids as well, reworked during several stages of deformation and metamorphism from F1 to F2, F3. So it's very important also for metallurgists to find, this will give you a guide also then for mining exploration or exploration. And we could find the last event is the last ores are iron, lead, and that was what was mined at first. This is iron and lead And that's exactly in the detachment. That's why I was telling you, when they showed us the map of the galleries, it was a map of the detachment. And at some point, the detachment would be cut by a high-angle normal fault. Boom, the galleries would go down 10 meters. And we could trace that fault at the surface. Oh, that's why the galleries go down 10 meters. The guys, they were following the lineation of the detachment when they were digging. They knew geology. Probably empirically, but they followed the geology. Okay, that's for today. Does that answer your questions about structure, mineral? You see, it's tedious work, yeah? And you don't have to, if it doesn't work by the first step, you have to insist and really think about your data. So the next step, as I was telling you, would be to try to, with the same tool, microprobe, date or laser date the different minerals. And then you probably have, because argon will work on that type of minerals, and it probably will help, or rubidium strontium might also work, and we might probably get, let's say, 50 million years for S1, 40 for the S2, and 30 for the S3. I never tried that, but it was a question, yes?
With respect to this particular project, what can we interpret in terms of the geothermal gradient, like with respect to the minerals?
Yes. So it was, at first, you see here, we go from, I think that's a 15 degree per kilometer geothermal gradient at the time of subduction exhumation. And we go to 25, 30 degree per kilometer geothermal gradient. So we double, the geothermal gradient has doubled. And it goes with doubling the thickness of the crust. And it's linear. The more crust you have, the more uranium, thorium, potassium will decay, and it's a linear relationship. If you double the amount of uranium, thorium, potassium, you double the temperature. But it takes 20, 30 million years to do so, and that's what we're going to illustrate on Friday morning. And you are the second year students, huh? First year, wow. I'm impressed. Thanks very much for your attention. Oh, you have more questions? There was one? No, but that's it? Okay.